be explore future trends and such as multi-material and hybrid additive manufacturing technologies. And the expert for this session, Dr. Professor C.P. Paul ji. Uh, Dr. C.P. Paul is leading a research group in area of additive manufacturing technology at Raja Ramanna Center for Advanced Technology, RRCAT. He is recognized as one of the top 2% scientists worldwide successively for the last 5 years from 2018 to 2023 in the list prepared by Stanford University, US and published by Elsevier. Dr. Paul has 25 years of experience in research and development of laser additive manufacturing from system development to its applications in engineering. His research program focus on next generation additive manufacturing system and processes. He is instrumental in promoting laser additive manufacturing technology in India through collaboration with other national labs and reputed academic institutes by extending the original developed facility for experiment. He has published 26 book chapters. He has published more than 150 research papers in peer-reviewed international journals and presented his work in more than 250 international and national conferences. He has authored a textbook on additive manufacturing for undergraduate and postgraduate students. Dr. Paul is founded director of AIC PI-HAP Incubation Center of Raja Ramanna Center for Advanced Technology. He earned a PhD degree in mechanical engineering on laser additive manufacturing of engineering components in 2005 and was a research professor at the University of Waterloo, Canada during 2006 to 2008. His efforts have been recognized with many awards, including the highest DAE Excellence in Science, Technology and Engineering Award, Homi Baba Science and Technology Award. I once again thank you. I would like to thank Dr. Paul for this session. Over to you.
Thank you, sir. This is Paul speaking, and I'll just share the screen. Please confirm whether you are able to see the slide or not.
Yes, sir. Yes, sir. You share. Yes, sir. It is visible.
It is visible?
Yes, sir.
Yeah.
Yes, sir. Yes, sir. Very much visible, sir. Thank you.
Fine. So this is the thing that we are going to talk. And in my previous talk, I talked to you about how laser additive manufacturing is making the difference as an introductory lecture. Now this we'll be talking about design for additive manufacturing, DFM. This is a very big field, and we have done pretty good work in this direction. And then I'll be sharing with you. And specifically, it becomes important when you talk of the multi-material systems. So the content that we are today talking is about design for manufacturing and assembly. Now we have design for additive manufacturing. And what are the guidelines normally people has to follow to make it happen? So thing is design for manufacturing and assembly is important because these two parts are inseparable for the production engineers when we talk of the functionality and manufacturability. So at one end, you have to focus on functionality of the component or system that you are developing. At the same time, manufacturability is also important. So what happened is people started thinking on this, and we being the conventional engineers, we were pushed to develop our whole thought process in such a way that it is imbibed inherently in our thought how a component will be built if we design it. So the concept of design for manufacturing brought a big change. With the change in the emphasis, specifically in the introduction of uh, mass production of the components and various part, especially when we are talking of batch production or you're talking of assembly lines. The concept of design for manufacturing is further extended to ensure the interchangeability and repetition by including the criteria of assembly. So it became design for manufacturing and assembly. And this is really a thing which made stuff different. But there are the cases where the systems are only integrated, but they are produced at different locations, and then the designer has to work on design for assembly. That is a different part which is being done. And in all these cases, the concept was and more focus on fit, function, and manufacturing of the process that we are using. And based on that, all the rules and regulations were built by us and how we conceive. Now, today, we are not may not be realizing, because most of the times you may be drilling a hole which is not oblique. You always want to drill a hole which is perpendicular to the surface. That is inbuilt in us, and we are brought up in that way. So all these things are credited, but this is a theory that which is working behind our concepts and making the things to that level. So as far as the DFM involved, you should have a knowledge of manufacturing and design operation procedures. And finally, it reduces the product development cycle time, and it brings a lot of economical things into the picture. And definitely component size, shape, and requirement changes and ensures the desirability performance. In summary, the DFMA brought flexibility, cost effectiveness, reduction, and the complete expenditure as well as diminishing intricacy in the production process. And this has brought a leap into the development of different component and manufacturing. So if you see, it starts with the design concept, then we go for the design for assembly, how the different component will be assembled. Then we talk of what will be the material process selection and the cost estimation. Then we'll take the best design concept. And after that, we go for the design for manufacturing. And then we take it design for minimum manufacturing cost. Then we go for the prototype. And once this is built, then we go for the production. At the same time, if we are finding that there are issues in the assembly, then people take it back, modify it, and so that the production, the product structures become simple from the assembly point of view. At the second point, people also take that yes, the is a simple from the product structure point of view, but whether is it economy or not, or should we remove or add? For example, sometimes the designer's dimensions may be coming like some odd dimension. For example, it may be say 103 millimeter. Now we know that 100 millimeter is standard bar available into the market, or so you can always modify your design and size so that economicity of the things can be brought into the picture, and based on things can be done. Once the prototype is made, which improve just this is a basically proof of concept of the whole stuff that we built, and then we go for the production of it. This is the typical flow chart that we follow for the design for manufacturing and assembly. So these things have definitely changed the stuff and brought a lot of economic stuff, optimization in the material side of simplified the manufacturing of the products, and definitely without compromising on the constraints that is put by the manufacturing process and overcoming the whatever the constraints are being posed while they're designing the product. So this concept really moved out and had worked for many years. With the introduction of additive manufacturing, when we talk of the terminology called complexity for free, some of the things that we came into the picture is we have to think from additive manufacturing point of view in such a way that we are able to achieve really stuff in bigger way. If you see the way things are working on as like today, many of the things that we build, we have not changed the design of the component, considering the additive manufacturing as a process. But just, and earlier this was made by some conventional process. Now we are making the same with direct part, by directly using additive manufacturing. So that is the first stage of design for additive manufacturing. Then we are only replacing the process. Nothing is changed. And after that, what happened? Like once you see the part is made and built, and then we may go for the second level when we are focusing on the form of the component, not the function. For example, in the conventional manufacturing, we may be using some two parts to weld in during the process, and to support the welding, there are some features included in the part, which may be not required when you are making the part as a single component using additive manufacturing. So these features can be removed, and that is the second level of adoption and rules brought in, that is the adopt for additive manufacturing, where we are focusing on form and process, which is changed and replaced as compared to conventional production part. But if we want to derive the advantage of additive manufacturing, it's not only the form and the process, but we need to change the function, fate, form, everything. Function, fate, form, and process need to be reconsidered and defined. So this is the way whole thing have moved. And design for additive manufacturing is a thing which is the final sort of destination for the technology to move at. If we talk of the advantages, I can tell the advantages of these for a company can be the companies who are using additive manufacturing only for the direct part replacement, they'll be crawling with the technology, while those who are following the adoption of the additive manufacturing without changing the fit and the function, then definitely they are walking. And the people who are really adopting in a big way and changing the whole stuff in terms of the function, fit, form, and the process, then it is like running for a race. So these are the three steps that has to be considered, and we have to adopt additive manufacturing in such a way that we are able to achieve a quite good space in terms of running the race. So this is the concept which is brought into the picture. So when I'm talking of the first step, which is the direct part replacement, here we are changing only the manufacturing process. Earlier, like you were making something by casting or by fabrication. Now we are doing specifically for the components which are sort of obsolete, maybe some pumps or some particular components which are not supplied by the OEM now. You want to build it. So we do the reverse engineering of that, and the process is changed. Now we are going for the direct part replacement, but we are not thinking of how the other things will come and bring the things to the different level. But this has really simplified the product development cycle for us, because you had already one out. You just do the scanning of the part, make the data cloud, and then build the surfaces and make the whole component. And then just see wherever the part worn out, you can have some additional surface brought there, and the whole reverse engineering can be done. And the component is ready in the virtual form for the additive manufacturing. And then we apply to this, then this becomes the simply production of the part without much change into this. And that is the way how direct part replacement is changing. Now, in this particular thing, when if you want to reduce the cost of the material uses, people are just thinking how the complexity of the process or can be removed, whatever is put into this, and the number of the parts which are brought into this are also removed. For example, one of the classical example that people talk of, the GE's fuel nozzle, it had 52 parts. When it was made using additive manufacturing, they are reduced to one. So what is happening, a number of stages that we are is removed, and that is the way whole thing can be brought. And that is the idea when we are talking of the step number 2, which is adopt for the additive manufacturing after improving the things from the direct part replacement. But I already told to you, if you want to go to the final phase of the adoption of the technology, we need to focus on form, fit, function, and the process as a complete freedom. Like we should start thinking in a differently, so that model we have to really forgo the things that we learned as a conventional manufacturing engineer, but try to bring the concepts of additive manufacturing imbibed into us so that we think differently and take the advantage of the full potential of the additive manufacturing, specifically by employing the concepts like generative designs, topology optimization, and bio-inspired components so that this becomes a very attractive technology for making the components. If you see the whole process, the design process is moved from design for manufacturing to feature-based design and manufacturing. Means today people are not thinking about what is the material they want to use. They are focusing what feature they want to use into this, and according to the feature, they can think of bringing the different material into it, and that's the way the new paradigm has come when we are talking of feature-based design and manufacturing. For example, in a part, you can have multi-material concept. For example, you can have two different material, like wherever you want to have better uh, cooling, you can use copper as a material. Wherever you want strength, there you can use steel as a material. So the combination of this is like we are not thinking a lot about the material, but focusing on the features that we want, and according the whole product is built and made into this. You see here, you see this particular component here. These are the part which is made into this, and you can remove the porosity and give the only feature that you want. So as a result, you have a really very good reduction into the weight of the part just by making a lattice filled design. Though the externally everything looks the same, but hollow and porous has really saved a lot of cost and the production time while fabricating the components. Another concept is, for example, when you are working on a design, say that you see the first conventional bracket, which is built, and when they did the optimization, topology optimization, they could reach to the optimized design, which is the altogether a different concept, and the technology is used. So what are we doing is, while making additive manufacturing, we are not making the conventional bracket, but taking it to the optimum shade, which is very attractive. And the design is basically focused on the stress flow in the material, which gives the advantage. This. And making an optimized design using additive manufacturing is not challenging. While if same is built by conventional method, then a lot of things has to be brought in. There can be case when we want to have higher surface area per unit volume. So to increase the heat transfer, we can think of using aluminum heat exchanger of the racing cars, how complicated things are built, especially if you focus here, very nice fins are built. These are not possible by conventional method. And again, this is the output of the finite element design that the people use as a tool to design the components. It is possible to have mass customization, like you can have hundreds of the custom dental implants built in the single belt. So these are the things how you are doing the nesting of the different part you have and going for the mass customization and building in a one way is also making the difference as far as the design for additive manufacturing technology comes. See, if you want to make a bicycle and then you see the frame has having bricks on, and we need not to build whole stuff the way it looks. You can always make a small part by breaking the components and bring it to the size we are looking for and join them together. Here you see the left hand side and the right hand side, we have a bike and how the frame is built in a beautiful way so that in the lesser time, the whole component can be built as a single unit and later it can be trimmed off and joined together so that desired design can be achieved. So this is the way how design for additive manufacturing has to be thought. It's not of the making the whole assembly in a one way, but how can you make small parts which falls within the built volume of the machine, built envelope of the machine, so that the component can be built to the next level. So what is happening when we are talking of these five different ways of doing design for additive manufacturing? We have to have some rules in our mind so that we can proceed and make the things into this. The first concept is part orientation. Now we have to think of the part orientation as the alignment of the CAD model on additive manufacturing build plate, and you have to make in such a way that the support structure required to build the component should be minimum. At the same time, the slicing surface, because it's well-known fact, the surface quality on Z, the vertical plane is better than the horizontal plane where the components are built. So if you want to have really good surface finish, so you have to bring it to the vertical plane. But the component size may be like that it may not support. So slicing strategy has to build in such a way that it helps. At the same time, we have to go for a really optimum toolpath generation, because in my last talk also I told that we are making a change of orientation by 67 degree in every layer as a standard practice, so that the residual stress and distortion can be reduced. And here we have to focus on the toolpath generation, so that the different components, specifically when you're talking of different section within a layer, how it's going to, this has to come in your mind, and we are focusing specifically for the part orientation. So for example, if you want to build a turbine blade or fuel nozzle, accuracy and surface quality is important. Accordingly, you have to design. At the same time, we have to think on those lines, like how are we joining, how the various surface will come over. And it's not the imagination and visualization of the final product, how well it look like, but during the process itself, how the main design can be disintegrated or reoriented in such a way that it leads to optimum fabrication time, optimum use of the material, least support structures, and definitely the surface quality should be the way we want, in a better possible, the best possible way. Therefore, part orientation is application specific, and optimum orientation is selected mostly focusing on build rate, surface quality, and support conditions required. Now, support structure is required to build a component, specifically if it has got some overhang structures. For example, if we talk of making um, some overhang structure and you want to work on it, then people use it some other material into this, and these materials are normally sacrificial material, and the joining with the main part is also thought to be least possible, and they should be easily removable. And specifically when you are doing a lot of uh, support structure, it should facilitate the fabrication of complex geometries, and generally removed after the completion of build process. So it is such a that the complexity can be, and we should be able to easily remove after completion of the build process. And definitely the support structure, if you are involving the more support involvement, is resulting into extra build time and post processing steps. Therefore, we should avoid having support structure. It should be as least as possible. This is also the criteria for design for additive manufacturing, which we need to consider. I told you the surface quality, the angle, these things are to be made in such a way that support structure should be brought into this. In general, you can always think of reducing the support structure in additive manufacturing, but it's not possible to make it zero. because of the complex geometry of the component that you are building. Now, how do the people make different type of structure? Specifically, when we talking of CAD model using pre-processing softwares. So, in general, people make the three part of the component. For example, there are three geometry locations like down skin, inner core, and up skin, and people do fabricate different type of the support structure so that post-processing steps can be reduced and brought to a different level. For example, there are three type of support structure widely used. For example, we have a sparse, surround, and smart. And you can see that sparse is the best possible if you have some inverted L to be made. Sparse is good. You see the support structures really come up nice. Surround is really difficult because you have L surrounded by the all support structure. Because in this particular figure, the support structures are shown in blue color, while the part is the inverted L, which we are going to build. And whatever the filling we are doing for the support structure, in all the criteria like sparse, surround, and smart, this can be in form of zigzag, lines, concentric, grid, or triangle, depending on the application. And most widely, people use lines, so the thing can be easy to work on. So when we talk of support structure in metal additive manufacturing, the most of the application of support structures to build a component which are having overhang structures. It also used to transfer heat from the top layer to bottom layers, and so that overhang bull structures are not. For example, if you make a very fine and thin support structure for supporting any surface, so again, you have to think on how well it take care of the heat when we are going for multi-layer deposition, and we have to think on those. Specifically, when you are making the support structure, we also have to think how are they placed so that the warpage and build failure can be reduced, and specifically the cumulative residual stress which is generated during the process can be brought down. So that is also the part of the support structure people think on directly. When we are talking of powder bed fusion system, the movement of the powder restoring unit, or what we call as rastering, that we have to take care of so the thing can be brought and led. Most of the times, hollow structures are used to define support structure so the thing can be made into different way. You see, in some of the companies, people use the primary support structure and the secondary support structure. The primary support structure are generally generated into the using standard software, the modeling software using some user-defined features. But when it comes to define the secondary support structure, they are to be taken care, specifically using pre-processing software in the support generation options in the software. For example, you see the effect of orientation we are talking of. You see the first figure here, the downward sloping phase again decides what will be the support structure here, what is the surface quality we are talking of here. Other thing is, if we talk about this circular geometry, here you see you have a circle while you have a rectangle here. The surface we need as an overhang structure here is going to help and decide when it is likewise. So depending on the geometry and the type of the component we are making, we have to think of how the support structure will help to make the things in different format. The support structures are normally block type. You see the different cache has been made. Then it can be point type. You have it all the four supporting from a one website, a complex web, and contour type. In general, support structure is required when overhang angle, the critical angle that I am talking of, is this particular critical angle is less than 45 degree. If it is more than 45 degree, mostly people are able to manage without building the support structure. Now, if you compare the support structure with the surface roughness, you'll find how the component comes. For example, if any support thing is there which is less than 45 degree and you want up facing and 0 degree up facing flat, so if you make it, you find very high roughness comes. On the other way, when you make it 90 degree to 45 degree up facing, the roughness goes down. And similarly, here, when you have minus 45 to 360 degree, the same thing comes out, and we have to think. So this is a way how the orientation makes the different type of support structure.
पटेल ये
Hello, Sandeep Kumar. Please mute yourself. Sandeep Kumar.
If you are making a component and then in the component there are different holes which are available, up to 0.4 millimeter, you don't need any support and they go very well. But if you are making anything which is less than 0.4, we need to be, take some precautions while making metallic additive manufacturing component so that the hole comes properly. 6 millimeter not required, but any hole which is more than 10 millimeters, you need to give support structure in general in the design aspect, so thing can be done. Circular holes are not a very good concept for making additive manufacturing. Always there is a thrust, can it be a teardrop or diamond, so that these things can be used and make the things in a very supportive format. So what we want to say that if you want to have option to have a circular hole or a teardrop hole, so in the direction of building, we'll be preferring teardrop hole and or a diamond shape hole, so the thing can be taken to the next level. Now, as I already told to you, ellipticals can be built about 25 millimeter tall if the height of the ellipse is the twice the width, and same teardrop shape holes of the combination of circular portions and the straight line portions as a peak can be built in this. And teardrop and the diamond profile are commonly used in the fluid channel as they are having comparable hydraulic performance. You must be knowing when you do the fluid dynamic design, then you must be using hydraulic diameter to identify some of the things. And here is the same. If the holes are required exactly round in the 10 millimeter, then it is advised to build a hole of 9 millimeter less than 1. And requisite size can be built in the post-processing format, or anything which is more than 10 millimeter, you need to have a really surface support structure, so which will make the things different to different format. The layer thickness and the build rate is the second thing that we need to focus on. And to do this, you see, if you have a higher layer thickness, then there would be stair stepping effect coming in. Though the build rates are good, but removing stair stepping effect will also cause extra post processing time. Then we have to really optimize how to take care of the stair stepping carpet or go for the lower layer thickness. So that's the way people decide and define on this. In general, lower limit of the layer thickness is governed by the maximum powder particle size that we are using, maybe powder bed fusion or direct energy deposition in any of these things. At the same time, the higher limit of the layer thickness is defined by the track aspect ratio. You must be knowing in most of the cases, the track aspect ratio means the width of the track divided by the height of the track while depositing the material has to be more than 5. Otherwise, it will lead to interrun porosity. So this is the way how the layer thickness defines and build rate is taken care with the stuff. There are also issues as far as the minimum wall thickness and the ribs are concerned. There are guidelines people have built on this. For example, if you are making a basic building block where you have some design and you are more bothered about the uh, distortion and components about the weakness, then if we have to focus in lot of these things, and in case of the laser, the diameter of the energy source or the nozzles define the wall thickness in a big way so that it supports us stuff. In general, the values for metal additive manufacturing is in terms of zero point 0.4 to 0.6 millimeter is fine, and in polymers, 0.8 millimeter thick wall can be built easily. This is the number which is available so far. In general, in polymer manufacturing, we are using mainly in material extrusion process like FDM. You cannot go less than the twice the diameter of the nozzle. For example, you are using a nozzle of 0.4 millimeter. The minimum wall thickness you can go for is 0.8. So that is the minimal correa people think and go ahead with. Another thing that comes into the picture is how the perpendicularity of the surface are good, and there may be distortion or deviation in while meeting the L-shaped structure and wall, which we want to be the perpendicular of this. So therefore, people what they do is they give some ribs which is used to distribute the forces while making the things and reduces the stresses and reduce the distortion, and this is the thing which it reduces to minimum material wastage and time. So if you talk of making a minimum wall thickness and the ribs, suppose you have a thin wall as I have shown you here, then people go for making a rib so that thing can be built. And thickness of the ribs are normally 75% of the wall thickness, and the height of the rib has to be less than the 3 millimeter of the thickness. Rib spacing has to be greater than the 2 times of the thickness, and fillet the point contact should and the rib and wall decides on many of the parameters. So this is the way how minimum wall thickness and the ribs are built in general in the plastic as well as in the metal additive manufacturing. Another thing that defines the size build volume of the machine is the maximum part size that you can build using it. And whenever you have larger components which are marginally larger, then you can think of going for the scale down components. But if it is not possible, then you have to break the component into different segments and put them together in such a way that the overall fabrication size or build time is low. So that is the concept that decides the maximum part size. Many times happen that you may be one design may be a bit out, maybe it's by 2 millimeter or 3. Then at a time the design review can be done and accordingly component can be built. It is very true that the large size component can be built using directed energy deposition and material extrusion process, and other processes are not competitive, which we need to understand, and this is the thumb rule for the as a general guidelines for design for additive manufacturing. When we are talking of making the different components, definitely material also play a role, because the material thermophysical properties and material compatibility when you use different material, they plays a role, and it is decided basically what type of applications we are using, what is the minimum feature size and resolution that we want, what are the certification criteria, and how the machining allowances are placed in the different part of the different surfaces within the company. So these are the things that we need to work out and make the things in different, and material considerations are very much important for making the different shape in this part. So in general, the thumb rule is avoid dissimilar material parts, because the dissimilar material parts creates a lot of stresses at the different level. So people want to avoid. Then second is if single material part is made, then it's good. And people do not go for the dissimilar material for the two parts if the function does not demand it. Reduce the use of expensive materials if the application allows. For example, you can have a core with some material and the surface can be from other one, so that if our application demands only surface property, not the bulk properties. And implementation of hollow or lattice design for expensive material of the economic consideration is also important. So these are the things that we consider as a design guidelines for additive manufacturing, especially focusing on the material consideration. There was a discussion on the residual stress during additive manufacturing. So we have to focus on temperature gradient mechanism rather than a full this. For example, I always talk to the student and we say that if you put whole plate into in a furnace, the whole component is heated, and when it is cooled, whole component is cooled. But this is not happening in the lasers. What happens is when you put the laser on a substrate, the substrate gets expanded because of the temperature here, the locally, and you have a stress coming on that. But what happens the moment the laser melts the material in the molten conditions, all the stress which are developed during the heating process becomes zero. And when the laser moves out from the location and there is a cooling of the substrate, and here you generate the stresses which are tensile in the nature. So that is the thing that we have to, sorry, compressive in the nature that we have to think of. And we have to think of how this can be reduced by pre-processing, processing, and the post-processing. Specifically, when we are talking of residual stresses, what should be our strategy which will make the things comfortable for us to move and work further. For example, if you want to use some pre-processing methods, you can have some stress concentration crack. Here you are likely to happen. You can remove wherever you have some uneven thickness. We also try to avoid the large masses for the deposition, and large change, abrupt change into the cross section. This will help us, and this can be done by filleting all the position. For example, if we want to make a component with us here, as shown in the stress concentration track, now you can move it to this level, which will have sharp, not sharp end, and stress concentration are less. And this is a design which is preferred as an outcome of design for additive manufacturing. When we talk of the residual stresses, we need to think on the different processing method. For example, you can use Mender and the rasting. Here you have all this. You can also involve strip, like you have two strips filling, and you can have chessboard. And these chessboard, whatever we are talking, every layer can be moved by, every rasting pattern is moved by 67-degree, and it can be brought it, whether it is stripe or chessboard or Mender, this is possible. Residual stress can also be further reduced by having a reduction in the thermal temperature gradient. So by providing a preheating build plate, and then things will remove and make the better to us. Now, if you see the comparison of various things that is happening in terms of wall thickness, support for over angles, holes, clearance, and minimum angle for the various process. For example, material extrusion, watt polymerization, powder bed fusion, material jetting, ballistic jacket, and DD. So these are the parameters. How does it work, and different possibilities. Now, when we talk of the powder bed fusion systems, specifically with the metal additive manufacturing, the two type of the technology which are available is the laser powder bed fusion as well as the electron beam powder bed fusion. And now you see how these two technologies stand for each other in terms of the orientation, like you have up skin vertical, smoother, down skin rougher, while you have the similar stuff for electron beam. The difference specifically comes when we talk of the wall thickness. In laser pure powder, you can have the minimum wall thickness in the range of 0.3 to 0.5, but in electron beam, you have to go 0.6 to 1 millimeter. And similarly, if we talk of the clearance, we have to keep 150 microns clearance in assemblies and 1 millimeter in the parts, while less than 1 millimeter in the parts to remove the powder particle. So there things are, if you compare the electron beam powder bed fusion as with the laser powder bed fusion machine, then laser powder bed fusion machine scores many positive points. But in terms of the fabrication time, the electron beam powder bed fusion machine helps and makes us to the next level. You must be knowing that a lot of things are being called in terms of the topology optimization, means we are optimizing it iteratively the shape of the component purely based on its functionality. And this is a new trend in the design. A lot of things are being done. Earlier, there was a limitation in terms of the fabrication of the components, but now with the additive manufacturing, things have changed and topology optimization is on the peak. So we use some numerical tools without taking the manufacturing process account based on the mechanical criteria to be optimized in a given design space, and then we allow to change this. Topology optimization technique not only permits the geometry change, but also the topology of the components which are being fabricated. Uh, the aim of topology optimization to have optimum material and the void distribution inside a particular design area for a given set loads and the boundary conditions. And for that, people use these technology for design of the building lightweight materials, completely organized design for manufacturing, reduce time to market, reduce usage of material, reduce usage of process energy, and eliminating the prototype stage. So all these are the advantage how prototype topology optimization is making difference as a part of the design guidelines for the additive manufacturing. So what we have to do, we have to do the first is prepare the problem statement, define the goals, collect the data and information, then define the identify the design variables, then go for the optimization, then apply the constraints and build the command. For example, you want to use a nominal start track camera bracket, which is like this. If you design space, if you do and start optimizing using FEM, then the probably optimum design comes out to be like this. You can build this using additive manufacturing and do the testing, and things will come. And this is a aerospace bracket which is built. So earlier the bracket was like this. Now it is changed to this. And if you compare these two, you'll find the star tracker camera bracket. The size has become small, cute, and better, and the lot of flexibility is provided, which is not the case of other one. If you talk of the conventional front suspension system of a transformer vehicle, then you'll see that how the transformer use the weight, especially vertical fishbone front suspension components, by reducing the material quantity by 40%. You see here, the conventional, it is built like this by using the pipes and all. But if you do the topology optimization, then it can be brought to this level. You see the grids have come, different parties come, and not only the strength, for the same strength, the material is reduced by 40% just by putting a critical fishbone front suspension into the different shapes and formation. The ultimate tensile strength greater than 1100 megapascal and 99.7% density for the titanium parts are providing a multi-part hand assembled steel structures for various applications that we are talking about. Now, suppose you want to make a spinal implant. You see the spinal implant here. Normally, people go with the grade 23 material for the making the spinal as recommended by FDA, and just test it for the chemical properties and then mechanical properties, and then we can devise the whole stuff in that way so that it works as a spinal implant. And this is the requirement we are doing it. As far as the body parts are concerned, it's a premium segments. A lot of things can be replaced and made, where things becomes good and easy for us. Another example is to make a knee joint for cat. You see in the United States, at the age of 9, one left hand leg of cat was damaged because of the bone cancer. It was cut and the leg was put in as a stifle with an artificial one, and people designed using mimics of materialize and printed the head with using EOS machine using the powder bed fusion technology, and this built. And after that, these bones are put into her leg after a operation surgery of 6 hours and a long rehabilitation. Now cat is comfortable with the new design and no sun's cancer is developed into her its leg. So this is the way knee joint brought and changed into this. So what do I want to say with you guys is today we learned how the things has been used interchangeably and repetition in for the design for manufacturing to design for manufacturing and assembly. But these are not achieving optimum design through conventional manufacturing. So therefore, this brought some new thing into this, specifically in the way of design for additive manufacturing. And additive manufacturing can be achieved by modifying the process for the manufacturing or form or not function of the component of the suit additive manufacturing. And the third, say, complete transformation in terms of form, function for the strict redesigning. But design guidelines that I have discussed are the essential facts and figures for the designers to design the different components on the additive manufacturing. And all these should work as an input and the back of the mind while making the components. And still, whatever I talked in terms of additive manufacturing is a art, not the science yet, because still we have a very long path to go. Technology is only some 35 years old, and other technologies have already crossed more than 2 centuries with the human. So we have to work on. Definitely, they have a many advantage in terms of topology optimization. It is providing tremendous freedom by using the effect of by deploying the additive manufacturing in terms of design and achieving cost saving and material saving. This is the with this I stop. Thank you very much. The session is now open for the discussion. If you have any query, I'll be happy to answer.
Hello, good evening, sir.
Yes, good evening.
This is Dr. Gaurav.
Yeah, Gaurav, please.
Sir, any comments on production speed and material limitations in laser additive manufacturing?
See, if we talk of the production speed of a typical 2 kilowatt direct energy deposition machine that is built worldwide, the deposition rate we achieve in the range of the production speed that we get is in the range of 6 to 20 gram per minute. While if you go with the powder bed fusion machine, the speeds are in the range of 2 to 10 gram per minute. That is the figure that normally people getting it. So powder bed fusion machines are relatively much slower as compared to the direct energy deposition machine. As far as the material considerations are concerned, we have to check the compatibility of the dissimilar material when we are using. For example, when you talk of building, we were working with a job like molybdenum deposition on the copper chromium zircaloy. Copper chromium zircaloy and moly are not having metallurgical compatibility. Then what we just thought, we brought a layer of nickel between these two, because we know that moly and nickel are compatible at the same time. Copper chromium zircaloy is compatible with the nickel alloy. So we're just bringing a one layer thickness of 0.2 millimeter, change the game. So when you're designing, definitely the thermophysical properties and the metallurgical compatibility of these materials are the thing that we have to look for, and accordingly we have to design.
Okay, sir. Is it suitable for mass production, laser additive manufacturing?
See, you should not compare laser additive manufacturing with the assembly line that we are making the car and other things. We should not compare.
Okay.
But you just say, if you have one or two machine in Amritsar for building the dental implants of titanium or other stuff, and all the people who are getting the dental implant fixed in their in the mouth, all orders can be brought to it, and hundreds of the dental implants can be built in one way. So in a one way means in a one batch. So that makes the thing very attractive and cost. So if you want to make a dental implant by hand one by one, probably the cost of making implant would be much higher than making all together in single batch in powder bed fusion machine. So I will only say that it depends on the case. Definitely, the speeds are not as comparable what we are talking in conventional manufacturing, specifically when we are talking and focusing on the assembly line. But wherever the customization is involved, this technology has a lead.
Okay, sir. Thank you.
Thank you.
Good evening, sir. Dr. Anas this side. Sir,
Thank you,
I
Prem.
have one question that how this adhesion strength of these different layers can be measured. Since we are creating a 3D from 2D different layers, so how we can evaluate the critical adhesion strength of these different layers? Is there any way, sir?
There are two ways the people measure. Okay. Uh, One is you make the uh, micro samples and test them so that you know that what is the difference in those. And especially, because if you make a large component, large samples specifically as per STM E8, we may not be able to do justice with the process. Then you have to go for micro systems. Another way of testing it is people use a ball punch method, in which what they have they have a circular hole, and they push a punch onto it, and you have a dissimilar material joined together, and we are focusing on the tearing of the this. So all these techniques are used, but again, these are the non-standard techniques, but giving a really good insight about the thing. And normally, if the process is standard, then no, if you have adopted the strength in the application of the dissimilar joint, then we'll be more focusing on the reproducibility of the component, and there is we will be focusing on whether something has gone bad or not in the this joint. So all these things can be achieved by the method that I have described to you, Anas. Thank you.
Thank you, sir. Thank you.
Sir, I have one question.
Yes, please.
How does layer thickness affect the surface finish and strength of a printed part for which are for adaptive manufacturing?
See, this is a really, very good question you have asked. See, in powder bed fusion, we use the layer thickness typically in the range of uh, 30 to 50 micron, typically. And the reason for using this is because if you melt the material in the range of 30 to 50 micron, we are able to melt whole stuff, and we ensure that everything is melted during the process. And there is some criteria of aspect ratio is also met, because if you want to have a very fine features, you'll go with the maximum 200 millimeter of the beam size, or 250 millimeter beam size, and then 50 micron is the number that defines your W by H is equal to greater than 5. So this criteria also helps. Therefore, the layer thickness is brought into this range. But if you talk of the DD, directed energy depositions, we are going a layer thickness from 0.2 millimeter to 0.5 millimeter, because in 0.5 millimeter, we can straightway increase the beam diameter to 2.5 millimeter or so, right? So this is the way it works. As far as the layer thickness is concerned, I'll say that if you have a very fine layer, the surface quality comes out normally good, because the energy utilization, melting of the materials are very effective. But as you go up, there is chances that you may have some ablated material around, or some material which are, jumping from here and to there, and we call it the use of rebonding wood. So all these things happen, and then the process is very dynamic, and the flow field in the powder bed fusion machine while on the bed is also playing a great role into this. But again, these are not the things well reported in the literature. But again, definitely lower thickness gives the best result as compared to the high thickness.
Thank you, sir. Thank you.
I think Harman Singh wants to ask something. Yeah, please. How does AM enable customized product manufacturing? Herman, this is really good. I meant to say I already discussed with during my this Q&A session that suppose you want to make thousands or maybe hundreds of the dental implants, and you know that if you are dentist and the dental implants are normally made by taking uh, virtual imaging or by taking some X-ray imaging of the teeth that we need to have. And here you can have hundreds of the maybe 50 or 100 dental implant placed together and make it. So here we are going for the customized dental implant for each patient in one go. That is possible, right? That is big important one thing. Second thing is if you talk of the bioimplant applications, the bone density that we have is the function of our sex. The ethnic we have, the type of the work we do, the food habits we have, all these things defines the bone density of our bones, or bone density. And when we are making the implants, presently, whatever the implants we are making, they are made with a solid block, and the density of titanium is 4.5 gram per cc, while the density of the bones are in the range of 1.5 to 2.7 gram per cc. So this is the difference between these two bone and the implant. So what happens is when you use a material and you do not customize the implant and change in the design in such a way that it meets the density and the strength of the material, there is some problem called stress shielding, which makes the life different for them, and it results into the failure of the implant. So we have to focus on this. Definitely, customization becomes one of the basic requirement in such applications, and it can be done by laser additive manufacturing. Limitation of additive manufacturing in terms of the speed and scale, as it is asked by one of our friend here. See, scalability is now being taken care, because if you talk of the powder bed fusion machine now, people are able to use about 49 galvanized scanner together, placed parallel. And if you talk of the dimension that I'm talking about, is it will be in the range of 2 meter by 2 meter. So that is the size we are talking, and all the components can be built in this. Height was never the problem in powder bed fusion. DD, it had been, you can have multiple head depositing different way, it is possible. So now scalability is now taken care. Speed I'm talking of, definitely we cannot compare with the conventional manufacturing like casting and other stuff. But what is more important for is when we are going for making a prototype or first component, or you have a limited volume, and if you consider the whole cycle time from design to complete fabrication, in that case, additive manufacturing has an edge. So this is the thing that we have to consider to go to into this. Another question is about possibility you see in additive manufacturing replaces traditional manufacturing. What is the challenge that we face in it? See, this is not going to happen. It is very long way to go and think on those lines, because traditional manufacturing is still having its edge and strength. But what will I say? These will go together so that thing can support each other. New features can be brought into the design, and manufacturing can be made easy. So that sort of thing is important. Amit is asking about the future of additive manufacturing. Yes, there is a good future because again, if you talk of Industry 4.0, additive manufacturing is one of the pillar driving the Industry 4.0. Specifically, when you talk of building a components, and if we talk of making a component in the maritime application, or if in the space application, you need not to take any spare component, or you are trying to make anything into the space stations. So all these things are possibility. You just take the raw material and whatever the components are failed over there, these can be built in no time or maybe very less time. So all these things are possible, and definitely it's going to bring a change into the whole paradigm. And can we replace the traditional forged components with additive one? See, for some of the material, the strength comes out to be better than the forged one. Specifically, if we talk of Inconel 625, where we are able to achieve cellular microstructure, the material properties comes out to be better than forged components. So there is definitely case-to-case basis. We have to find out, and where it has a strength, we can go forward and make the things into the great way. Yes, Dr. Gaurav, you wanted to ask something.
What role did this shock wave formation plays in the material microstructure?
Please repeat your question.
Sir, shock wave formation, what role does it plays in the materials microstructure? Shock wave formation.
Short.
Shock wave formation.
Yeah, it plays a greater role, because what is going to happen whenever you have short wave means your material is absorption is more, cooling effects are faster, so it lead to very fine microstructure. So that really it makes the difference into that. It makes the difference.
Is there any correlation with the wavelength of the laser with this?
No, see, most of the material that we are using, especially in the metal additive manufacturing, are the presently the most efficient lasers are near 1 micron lasers, especially the fiber lasers, other stuff which are used. But going for the shorter wavelength like green lasers, which will be again the wavelength will be somewhere around 300 nanometers, and then if you want to go blue, where we are talking about around 250 nanometers. So as the wavelength goes shorter and shorter, the absorption of the laser in the material increases, and specifically this is very good if you are using high reflecting surfaces like copper and aluminum. But if you see the development in these laser technology, specifically you talk of making the green laser or making the blue. Today, the cost of 2 kilowatt fiber laser of the 1 micron will be costing you somewhere around 20 lakhs rupees, while the cost of 100-watt blue laser is about 50 lakhs. So though you have big advantage in terms of the shorter wavelength and absorption making the things, but still economics are not supporting it. Still people are very happy with the 1 micron, because if you talk of the 50 lakh you are trying to invest into this, in that you can have probably a laser of the 4 or 5 kilowatt power. So now comparing, like 100-watt blue laser and then 5 kilowatt 1 micron laser, then the fiber laser wins and its application goes into it. So that is the thing that is making the thing into a different domain. So definitely in terms of academically, blue and green are a better choice. But in terms of the economy, today even the 1 micron lasers are leading the path.
Sir, one more question. According to you, what is the major breakground application of this laser additive manufacturing till now? In repair or in some other
Repair
activity?
is for sure. Repair is good. Last time also I shared a very small story about how things are changing. See, if we talk of the all thermal power plants, they are aging now, and many have to be dropped down. For example, 60 years or 70 years are already done, and these power plants and many of the petrochemical stations, their companies have no more making that particular types of impeller walls and all these things, and we have option either to change the full wall or take out the part, go for the refurbishing. That is a really very good business that people are working. Specifically, another idea, if we talk of in armed forces, in all our guns, after firing, a large number of the shells, the idea of the gun, is eroded out. So you have to refurbish that. So these are all the areas where today people are just replacing that. And then now what we are looking for, can we go and deposit the material inside these shells, so that with some better performance material, so whole things will change. Again, this is the way the whole things are being thought of. Similarly, if I take you the application of the preparing of the gas turbine, the gas turbine blades you see in as each gas turbine, we have a more than 450 blades, and each blade is costing few lakhs. The repairing of each blade by GE itself takes around 1.5 lakh for that. Now if you have to refurbish whole gas turbine and you have a more than 450 blades and each is costing you about 1.5 lakh to repair by GE, you see the how much the volume, the business they are talking of. And if these can be done in India by reducing the cost to be in the range of say maybe 50,000 or say maybe 60,000 or 40,000, then definitely there's a lot of case for the repair and this opportunities. So a lot of opportunities are there we need to tap on so that things can be taken to the next level. Yeah,
Okay, thank you.
thank you.
Good evening, Dr. Paul.
Good evening, Bataiye, Narendra ji.
Sir, first of all, I'm really thankful for such a wonderful and informative session, sir.
Harpreet,
Sir,
Harpreet, please mute yourself.
sir,
Harpreet, please mute. Harpreet, please.
sir, how do thermal gradients in metal additive manufacturing process influence microstructural evolution and mechanical properties, sir? Thermal gradients in, yeah.
I got your point. See, what is happening, you know that mm, the microstructure, whatever we are generating, is basically the solidus liquid interface that we make it happen, right? So,
Yes.
when you're melting and material and moving ahead, and there would be solidification front velocity, which will be at the solid liquid interface. And how does it move? And from there, the microstructures start generating. So in general, whatever the scan velocity that we are taking up, for example, you are moving with a 0.3 meter per minute, or you are moving with a 0.1 meter per second for the powder bed fusion machines. So these are the things that defines what sort of the microstructures going to make the difference. As far as the preheating the plate or the temperature we are getting is concerned, do contribute in reducing the residual stresses, but in terms of the microstructures, prominently the microstructure is governed into the solid liquid mushy zone, that is there, and it doesn't last for long. So we are not able to change a lot of thing in terms of the time. So there is not a large difference, because so far we have increased the bed temperature to 500 degrees centigrade or so, and deposited the material like in inconel or the nickel alloy having melting point about 1500 degrees Celsius. But we didn't see a large variation in the microstructure. And reason is this that I told to you.
Thank you, Dr. Paul.
Thank you.
My one query is not related to the topic. If we really want to establish a lab, 3D lab in our campus, so what is required for that, and what would be the approximate cost we have to pay, sir?
It depends what are the things that you are looking for, and definitely now as a person who is heading the AIC at RRCAT, Atal Incubation Center at RRCAT, we have some startups working with us which can give you very attractive prices for making these machines. So what will I say, Narendra, you just give me a message or personal call. We can discuss on these. What are the costs you need to have? What sort of machine we are talking? What is your objective? What are the program that you are looking into this? Based on this, we can customize and we can match the funds that you have, or we can reduce the lowest possible for your application.
Okay, so my basic prime motive is that how our student should has to update themselves with the current industry standards. As you know, this is in a very, very important 3D printers for just to understand the current technology and requirements. So my prime motive is that, sir.
No, typically, if you don't go for a material characterization, like I understand that in that case, you have all metallography and other testing facility with you.
Yes,
Any
sir.
number more than once a year is good enough to have these machines with you.
Okay, sir. No issue, Paul, sir. I have your number and tell me the convenient time to call you. I will have a word with you in this regard and how we can pursue.
Yeah, see, unfortunately for you drop a mail, I will ask somebody to work on with this you and we will connect. Definitely, we can have even the virtual meeting on this part. But now February and March is a bit tight for me because of the examinations here. But
Okay.
definitely, we'll take it up one day because now we have a National Science Day, then I have Foundation Day, then I have a one conference aligned, then examination. So all these things are critically killing us. But
Okay.
again, we can take it up. We can take it up. Yes.
That's great, sir. Ample of task you have to manage, sir. So what about which conference you are stating, sir? Which conference is there?
We
It's
have
a,
we have a National Laser Symposium being
okay.
organized at Medicaps University here. Maybe I'll share the link in the
Yeah.
already there.
You please share the link and I will see that what from our faculty side we can contribute for that conference, sir.
Yeah, yeah, you
The
can.
still date is there and our last deadline to submit the paper.
We see how the things are there, and no, because though the dates are already done, but
Okay.
we can think of if something really good comes out,
Okay.
we
And
can think on those
right,
lines.
right. Is the conference proceeding is being indexed somewhere, sir, or sent for the journals, or it is in the
We are
proceeding
working on
only?
it, but I will say if you want to have something like that, then we are having another conference here at IIT Indore in the month of December. That
Okay.
is AMTDR. So that probably AMTDR also. TDR. This is being done. I'll just share you that link also. So if you can focus on those and things can be brought to the next level.
No issue, sir. I will just send you one reminder mail. I have sent the invitation for the lecture. If you do remember that, my mail is already with you, sir. But
Yes,
I
yes,
will again, yeah, I will send the reminder mail and we can discuss over there.
yes.
Thank
No.
you, Paul, sir, for this wonderful session. Over to Grupesh, sir.
Thank you, sir. Sir, I have one question. I
Yes,
asked you last time.
yes.
Which type of post processing can be done in additive manufacturing, and what is the parameter for same?
Food processing.
Sir, post processing. I'm asking post processing.
Post processing can be done. See, there are two ways to manage it. One is inside post processing. What happens is like recently, if you see, we had one published one paper in which we are doing sequentially heating of the layer after because what we do is we want to really thermalize everything and keep the thing. Then what are we doing is we are making 4 or 5 layer and then we are giving one heat run over there so that surface irregularities can be made. And this is really helping us specifically to make many features having overhang structures. So that is the way we have to work. In terms of the post processing, hipping is one of the commonly used thing that people do it, because whenever there is some small defect in terms of the pores and other stuff, that can be suppressed using hipping. So that is the one of the thing that people go for it. To improve the surface finish, people go for many things like to improve the surface finish, people go for many post processing like slurry clearness of this. Then now there are some magnetic emulsion process are there in which people try to improve the surface finish. And definitely conventional heat treatment is already there. You can use all these things to achieve the properties of the material.
Thank you, sir. Thank you, sir.
Gurpreet sir, one more thing I will add here is, if you see in our textbook, we have already dedicated chapter on the post-processing of the material. You can go through on those lines.
Okay, sir. Thank you. Thank you. Thank you, sir.
Thank you.
Any other question from your side, participant, please?
Sir, if possible, you can share the link of your book chapter.
I have no, I'll share you the book itself. Just a minute.
Okay.
This is available on Amazon and this particular book. I'll just share with you.
Okay, fine, sir.
This is the link of the book. Present price is not very high. It is, I think. Actually, when there was a COVID, and it was a challenge for me to keep all the research scholars busy during that time. And now the present cost is around, yeah, 1,000 rupees. You just see it because it's also available in the Flipkart. Wherever it is cheaper, you can go for it. So
No issue, sir. We can even recommend it for our library too, sir. There's
yeah,
nothing
yeah.
like that was going. So,
And again, this particular book is available. Is already recommended by AICT. It's a
okay,
recommended.
that's great, sir. That's great. For which curriculum, sir?
It is for UG and PG. Yeah, there is one optional subject in the third year for the UG, and that is called additive manufacturing. For this book is recommended.
So additive manufacturing is also included in the UG course by the
Yes,
AICT.
in AICT it is already there.
Okay, that's great, sir.
Mm.
So we'll definitely go through your book, sir.
Mm.
Thank you, Paul, sir.
Thank you.
Thank you, sir, for this great session. And we have learned a lot of things from your side. Very, very thank you, sir, for joining us.
Thank you. Thank you very much.
Thank you, sir. We will meet again in future. Thank you.
Thank you. Thank you. Bye bye.
Thank you, sir. Dear participant, please be online. Our next session will be start shortly. Please be online.
Dear participants, good evening. Our next expert of the day will join us shortly. So one important information I want to share with you that there will be a feedback link will be enabled in your ATAL AICT portal login ID, which will be enabled only after submitting the test. So test will be again available in your login ID at the ATAL portal by tomorrow. So around timing, if you'll go through the schedule, its timing is between 6:30 to 7:30 p.m. So accordingly, I request the coordinator, Dr. Grupesh ji, he will let you know in advance when the test will be available on the AICT portal, and there will be a 20 questions. So 20 minutes, as per the directions and guidelines of the AICT, 20 minutes will be given to you to attempt that questions. So after that 20 minutes, the link, you won't able to submit your response. So it will be purely on the AICT ATAL portal. No other Google form will be shared with you. Once time is over, it means we are unable, we will be helpless to help you out if we really want to do also. So it is a humble request and kind reminder to every participant that kindly attempt your test as per the time announced by the coordinator by tomorrow. It will be in between 6:30 to 7:30 p.m. And attendance, as you know, that to qualify for this certificate, 80% attendance is mandatory. So kindly attend all the sessions, those who have already missed any one session. So it is required for them, they should have to join accordingly, so that their attendance should has to be, they should qualify the minimum attendance criteria. So as there is a no role of the college side, so certificate will be also generated through the ATAL AICT portal. So you should have to complete the minimum attendance criteria, attempt your test, score minimum 70%, and fill the feedback. Additionally, we come to know that we should have, there is a requirement of the feedback for the lectures which are being uploaded on the YouTube. So that link will also be shared by Dr. Grupesh, coordinator of the FDP, by tomorrow. So you should have to go through the lectures. He will share you the YouTube link, and kindly fill the Google form, feedback form, which will be, link will be provided by the coordinator. So it is, so right now there is will be two type of the feedbacks. One is on the ATAL AICT portal, and another is for the YouTube channel, where the lectures of the expert which has been delivered is being uploaded. So I parallelly request to the our computer assistant, Mr. Suraj Kumar. He should have to upload the lectures as discussed, and he had already uploaded the previous lectures. After today's lecture, we will get completed. It will be uploaded accordingly. So kindly, participants, uh, you should have to give the feedback accordingly. So any information required from any participants related to this, we are open for the questions.